Every second, your body executes a biological sorting algorithm. It continuously scans trillions of cells to distinguish the body's own tissues from foreign anomalies. Self refers to your normal, healthy cells. These must be recognized, protected, and ignored by your defensive machinery. Non-self encompasses foreign microorganisms, bacteria, viruses, fungi, and parasites that must be identified for elimination. There is also altered self. When host cells become virus-infected or turn cancerous, the immune system must target them to prevent a larger systemic failure. Successfully identifying these three states is the foundation of survival. Failing to make these distinctions leads to either fatal infection or the body destroying its own healthy tissue. Before mounting a defense, immune cells must be manufactured and trained within the primary lymphoid organs. The bone marrow produces all blood cells from hematopoietic stem cells. It serves as the critical maturation site for B lymphocytes and key innate defenders like neutrophils and natural killer cells. The thymus is located behind the sternum. It is the exclusive site for T-cell maturation. Once mature, these cells execute a two-tiered defense architecture to protect the host. The innate system provides a rapid, hard-coded response within minutes. The adaptive system is slower and programmable, designed to learn and remember specific pathogens. At the moment of infection, or time zero, the first line of defense is purely physical and chemical. Skin, mucous membranes, and normal microbiota physically block entry, while lysozyme, gastric acid, and defensins provide chemical barriers that repel everyday threats. When these barriers are physically breached, the innate cellular defense activates within minutes to hours. Innate cells do not recognize specific individual pathogens. Instead, they use pre-programmed sensors called pattern recognition receptors, or PRRs. These include toll-like receptors, nod-like receptors, and Rig-I-like receptors, which are embedded in the cell membrane or floating in the cytoplasm. These receptors detect pathogen-associated molecular patterns, or PAMPs. Common microbial structures, such as the lipopolysaccharide on gram-negative bacteria or viral RNA, lock into these receptors and trigger an immediate alarm. This provides a rapid, generalized response, allowing the body to react to common microbial structures even if it has never encountered that specific strain before. PRR activation triggers systemic inflammation, which increases blood flow and recruits immune cells to the site of the breach. This process is marked by 5 classic signs: rubor or redness, calor, heat, tumor, swelling, dolor, pain, and functiolasa or loss of function. Phagocytic cells, specifically neutrophils and macrophages, arrive to begin clearing the area. During phagocytosis, these cells identify and firmly attach to the pathogen before physically engulfing it. The pathogen is trapped in an internal phagosome, which then fuses with a lysosome to chemically digest the invader. Phagocytosis clears local bacteria while providing the physical material necessary to activate the adaptive immune system. As the timeline shifts toward the 3rd day of infection, macrophages and dendritic cells begin converting digested pathogens into mobile biochemical data. Dendritic cells, macrophages, and B cells serve as antigen-presenting cells, acting as the bridge between innate and adaptive immunity. These cells route a digested protein fragment of the pathogen to their outer surface, presenting it as a chemical barcode using major histocompatibility complex, or MHC, molecules. MHC class I molecules are found on all nucleated cells. They flag internal infections within host cells, the altered self state, to CD8-positive T cells. MHC class II molecules are found only on antigen-presenting cells and are used to present phagocytosed external pathogens to CD4-positive T cells. These cells physically migrate to secondary lymphoid organs, like the lymph nodes or spleen, to find the specific T cell that matches the antigen, initiating the adaptive response. Within 3 to 7 days, the adaptive system provides a highly specific response. While slower to activate than the innate system, it possesses immense targeted power. Activation occurs when a CD4-positive helper T cell binds to the specific antigen presented on the MHC class II molecule. The helper T cell coordinates the immune response by releasing cytokines that activate both branches of adaptive immunity. In cell-mediated immunity, CD4 cells stimulate CD8-positive cytotoxic T cells to hunt down and kill virus-infected or tumor cells. CD8 cells release perforin and granzymes, forcing the infected cell into apoptosis, a programmed cell death that results in the cell imploding and fragmenting. This process focuses entirely on executing compromised host cells to remove the pathogen's environment. The second adaptive branch, humoral immunity, is mediated by B lymphocytes. When a B cell recognizes an antigen and receives a signal from a helper T cell, it proliferates and transforms into a specialized plasma cell. Plasma cells secrete antibodies that neutralize toxins and physically prevent viruses from entering host cells. There are 5 major classes of these immunoglobulins, each with a specific role in systemic defense. IgM is the first responder. IgG provides long-term immunity and crosses the placenta. IgA protects mucosal surfaces like tears and saliva, and IgE triggers allergic reactions and defense against parasites. While T cells provide direct cellular combat, antibodies act as a chemical dragnet, neutralizing pathogens before they can interact with a host cell. After the infection is cleared, memory B and T cells remain in circulation for decades. Upon re-exposure to the same antigen, these cells respond exponentially faster and stronger, providing the biological basis for how vaccines work. To prevent the immune system from causing collateral damage, the body utilizes regulatory T cells, or TREGs. TREGs suppress the immune response once the threat is gone, ensuring the defensive machinery does not unnecessarily damage healthy tissue. Ending the immune response is as biochemically complex and critical for survival as starting it. When these regulatory mechanisms fail, the body enters a state of autoimmunity. This occurs when the immune system loses self-tolerance, fails its baseline computation, and begins attacking its own tissues. This error results in diseases such as rheumatoid arthritis, systemic lupus erythematosus, type 1 diabetes, and multiple sclerosis. This matrix summarizes the two systems. The innate response is rapid and nonspecific, while the adaptive system is slower but builds highly specific, long-lasting memory. Human survival relies on the interdependence of these two tiers, the innate response holding the line just long enough for the adaptive network to successfully engineer a cure.